Hey everybody, let's talk a little bit about waves, and in this case we're talking not about waves in the ocean, but waves of energy along the electromagnetic spectrum. And so the electromagnetic spectrum is basically it lists and it contains all the types of radiation that exist in the universe. Okay, and there's 7 major regions. Okay, there's the gamma ray, there's the gamma rays, and then there's X-rays and UV, and then there's this little area here, which is the visible. Okay, so the visible spectrum here, IR, microwave, and all of this stuff down here is radio waves. And keep in mind that this goes on and on in this direction. In this direction, anything that's has a really itty-bitty wavelength are gamma rays, and the wavelengths can keep getting smaller. Here, really long wavelengths and really long that get longer, those are going to be radio waves. Okay, but all the energy or radiation in the universe falls somewhere along the spectrum. Our eyes, it turns out, are have adapted to just be able to sense the visible spectrum, which is somewhere from about 390 nanometers, just below that blue, so somewhere up to about 710 or 720 nanometers. Okay, so it's a very narrow range of light that we're able to see, or radiation that we're able to see. Okay, but that's all we can do. Now, some animals can see a little bit into the IR, some can see a little bit into the UV. But for the most part, this is the part of the spectrum that we can see. Okay, and so the other thing about the electromagnetic spectrum, or about this section, is that we're going to assume that light travels as waves. You may know that light can be considered both a particle. It can travel along as a particle, or it can travel as a wave. In this case, we're going to keep it as a wave, and so we're going to talk about what a wave is and what the properties of waves are in this video. Okay, so the first property that we want to talk about is wavelength, and a wavelength is actually a length, and it's measured in meters. Okay, and the symbol for wavelength is lambda. Okay, so when we see lambda, that means wavelength. It's like maybe a capital T that kind of fell over, or maybe it's a Y that's flipped up. I don't know, however you want to visualize it. I just know it as a Greek letter lambda. Okay, and the definition of a wavelength is the distance from the top of one wave, which we call the crest, to the top of the next wave, and that then is the wavelength.
Jacoby Smith, please report to the main office. Jacoby Smith.
Okay, now I get it, with light, the waves typically don't change length, so you can actually take it from trough to trough if you wanted to. That's also going to give you the wavelength. Or you can go from mid to mid. But we just always want to kind of standardize that length. So we always take it for any wave, we always go from crest to crest. Okay, we measure that in meters. And the last thing about wavelength is kind of the defining characteristic of the light. If we look here, notice that this scale on the bottom tells us the wavelength in powers of 10. Okay, tells you the wavelength of the character of the type of radiation. And again, notice that the visible light is about 390 nanometers, meters being the length, to about 720 nanometers, again, meters being length. And that's how we kind of define radiation, is by its wavelength. Every once in a while, we'll define radiation by frequency, and you can see that up here. Okay, and so things like radio waves, we'll say FM radio, 95.7, okay, 101.1. Those are those are wavelength, those are frequencies in hertz of the wavelength. But for the most part, we use wavelength in science class. Okay, now the frequency is kind of an interesting thing. Let's see here. Okay, because the frequency, I don't want to pause this thing. I want to get it to go. The frequency is how long or how fast something, how many times something passes a given point. So if we look at this, you can see that here one wave is passing this line every second or so. Okay, but down here you'll see that it's 2 waves that are passing this for every second. Okay, so this has double the frequency. Okay, and if you notice, it will also have half of the wavelength. There's actually a relationship between frequency and wavelength that we'll get to in a second. Okay, but I wanted you to see that. Okay, now the units of frequency are hertz. Okay, get rid of some of this junk here. Okay, are hertz, which we abbreviate Hz. Okay, like if we're talking about radio frequencies, 101.1, okay, is in megahertz. Okay, that's millions of hertz. Okay, a hertz is also equal to 1 over seconds. And if you're really a mathy person, you know that 1 over seconds, or sometimes we call it reciprocal seconds, 1 over any value is that to the -1. So that's where that comes from, seconds to the -1. The symbol for frequency is the Greek letter nu, the lowercase Greek letter nu. It is not a V. It is not a V. Okay, it is a Greek letter nu. And there, like I was saying, there was a relationship between frequency and wavelength. Okay, that as the wavelength gets longer, the frequency has to get shorter because there's less waves to pass that certain point. Okay, and so we can, like I said when I was talking about wavelength, we can use frequency to characterize some things. But given the frequency, we can definitely find the wavelength. So if we have a frequency of 10 to the 12th, we know that we're somewhere around 10 to the -4 meters in terms of wavelength. Okay, so that's new. Now amplitude is the height that a wave is off of the origin. Wow, that was pretty good. Okay, so this guy has an amplitude here, and this guy has twice the amplitude. Okay, so amplitude is, again, a height, so it's measured in meters, and its symbol is A. Now, a lot of times in chemistry class, we won't use amplitude much to describe waves because it's not part of the kind of the straightforward formulas or part of the straightforward properties that we want to deal with. In physics, we usually measure amplitude of waves. And then the last property of a wave is the energy of the wave, and that's probably the most important one, because the energy of the wave, it kind of tells you how strong or powerful the waves are. Okay, and so here are 4 choices of energies, waves. Okay, you can see that this has the same wavelength as this. Okay, but notice its amplitude is different. Okay, and this wavelength here is longer, and then this wavelength is shorter. Okay, the idea is that the shorter the wavelength, the smaller the wavelength, the higher the energy. Okay, so if we have something with a really short wavelength, like gamma rays, okay, they're going to be super strong, super powerful. And when I say super strong, super powerful, or high energy, I mean that legit can do damage to you. Okay, imagine UV light. Okay, UV is strong enough to burn your body. Okay, that's a sunburn. You're exposed to too much UV, your skin burns, you have UV happening. You have UV damage going on. Okay, X-rays is strong enough to penetrate your body. Okay, that's how you see bones, is that those waves go right through soft tissue. They get stopped by bones, but still, they're powerful enough to go through your body, which is kind of freaky. Okay, and then there's also gamma rays, which are super strong, and fortunately our planet shields us from a lot of the gamma rays. So the shorter the wavelength, okay, the smaller the wavelength, the stronger the energy. So this guy has the strongest energy, and this guy here has the lowest energy. These two have the same energy because amplitude does not affect the amount of energy. Okay, and so there are two constants that we always need to have handy when we're talking about waves, and that's going to be Planck's constant, named after Max Planck. Okay, and that is the constant that relates energy to frequency. Okay, and its symbol is H. Okay, and then there's the constant that relates frequency to wavelength, and that is the speed of light, and its symbol is C. Okay, I don't know why Planck's constant is H and why the speed of light is C, but they just are. Okay, and these are the values. You don't have to memorize them. Typically, I'll have them available for you. Okay, and so here are the three formula. Okay, it actually turns out that there's just two formula. There's just this one, and this third one is actually just a linear combination of these two. But here are the formula. This is energy equals Planck's constant, that's H, times nu. Okay, this gives us the relationship between frequency and energy, that as frequency increases, and that's what I'm saying here, it's a direct relationship. As frequency increases, so will the energy, because Planck's constant is a constant that's never going to change. Okay, and then it's an indirect relationship here between nu and lambda. Okay, as frequency increases, the wavelength decreases, and vice versa. Okay, because remember, C is always going to stay the same. It's always going to be the speed of light, 3 times 10 to the 8th meters per second. And then the last formula is this formula, E equals hc over lambda, and what that does is that relates energy to wavelength, and it's really just a combination of these two. Now I'm going to show you how I did it, but you don't have to be you're not responsible for knowing how it works. But here's what I'm going to do. Okay, I'm going to take C equals nu lambda, and I'm going to solve this formula for nu, for frequency. And so when I do that, I get frequency equals C divided by lambda, because I divide both sides by lambda. And so now this is equal to nu, and that can go right in there. So that means that we get E equals H times nu, which equals, make sure, E equals H times C divided by lambda, wavelength, and that's what that formula is. So this really isn't a third formula to write down. It's good to know if you want to relate wavelength to energy. But a lot of people don't give you this formula on any sort of exam, because you can figure it out from the formulas given. Okay, and again, this is an indirect combination, and we talked about this earlier. It shows an indirect relationship, because as this increases, the denominator of a fraction gets bigger, so that means the energy is going to get smaller. The longer the wavelength, the smaller the energy, and vice versa. Okay, so those are the properties of a wave, and goes over the wave, the formulas of a wave. So there we have it. Maybe we look at the next video and figure out how to use these formulas. Have a great day.